The equilibrium constant. So the equilibrium constant is a way to quantify concentrations of reactants and products at equilibrium. So we're going to look at this generic representation of an equilibrium chemical reaction. So we have the coefficients represented with lowercase letters and the reactants and products represented with capital letters. And there could be one reactant, one product. There could be 5 of each. It doesn't matter. And we use the chemical symbol inside of brackets to mean the molar concentration of that substance. So we've used that before. So this is what's called the law of mass action. This is the definition of the equilibrium constant. So the equilibrium constant for this reaction is equal to the concentrations of the products multiplied by each other. And they are each raised to a power equal to the coefficient. So D is raised to the power of lowercase d. And that is divided by the concentrations of the reactants, similarly raised to the power of their coefficients. Okay? So that's the overall big idea. Well, let's look at a specific chemical equation. 2N2O5 is in equilibrium with 4NO2 and 1 oxygen. We can write an equilibrium expression for this reaction. The equilibrium constant is going to equal the concentration of the products. So we've got NO2. So we put that in brackets. It's the molar concentration. The coefficient is 4. And so this concentration is raised to the 4th power. And then we've got the concentration of oxygen. That coefficient is an understood 1. And so we have an understood 1 as the exponent for that product. Those are the products. And then that's divided by the concentration of reactants. Here there's just one reactant, the N2O5. It's squared because the coefficient here is 2. So the coefficients become the exponents. And it's always products over reactants. I remember having a hard time remembering that when I was in school. It's always the products over the reactants. A little bit like delta is always final minus initial. So it's always the final on top and the initial on the bottom. Any questions? So here's a for practice. Express the equilibrium constant for the combustion of propane as shown by this balanced chemical equation. So this shouldn't be too tough. So K is going to equal, what do we put in the numerator? The concentrations of the products. So we've got CO2. And does that have an exponent?
Yes.
Yeah, so it'll be 3, right? This guy. And that's multiplied by the concentration of the other product, raised to what exponent? 4. And that's divided by reactants. C3H8. The coefficient is 1. And oxygen to the 5th power. That's it. Yes?
Since we can do equilibrium constant for the decomposition of N2O5, could we do one for, say, like radioactive decay, like in an enclosed space? Like maybe beta particles floating around?
That's a good question. Could we do an equilibrium constant for radioactive decay? I think that's one of those reactions where the reverse reaction is negligible. And so there really is no reverse reaction.
Okay.
Yeah.
Based off the word decay.
Well, what happens in a nuclear decay is that the atom itself is coming apart.
It's not going to come back.
And making it go back together is going to require a great deal of effort. It's not going to happen spontaneously by itself. So, good question, though. Any other questions? So I mentioned this at the beginning, but let's talk a little bit more about the significance of the equilibrium constant. When K is large, and by large we mean much larger than 1, okay? Here's an example, K being 1.9 times 10 to the 19th power. That's a big number, right? 19 zeros, really big number. Here's the equilibrium expression for this. If K is equal to a large number, what does that tell us about the relative concentrations of products and reactants? The products must be high and the reactants must be low, right?
Yeah.
In order to get a large number here, the top has to be big and the bottom has to be small. So that tells us that this situation favors the forward reaction. So we're going to get a lot of product and we're going to have very few reactants left. You're almost never going to have a situation where there's 0 reactants left. You might get down small enough where you can't measure it, but there's probably going to be at least 1 molecule left, right? If K is very small, here's an example, 4.1 times 10 to the minus 31. Mind-bogglingly small number. That indicates that the reverse reaction is favored. So if we look at the equilibrium constant expression, and this is a very small number, that tells us that the numerator is small and the denominator must be big. To get a small number, you take a small number and divide it by a really big number. You get a really small number. So small k tells us there are going to be more reactants at equilibrium and very few products. The reverse reaction is favored. Now this is important. The equilibrium constant says nothing about how fast a reaction reaches equilibrium. It could take 5 years to get to equilibrium. It will get there eventually, and the equilibrium constant tells us what will happen when it gets there, but it says nothing about how fast. Those are two different concepts. So, summary, K being very small, reverse reactions favored. If K is approximately 1, and these are not, there's not really a dividing line. You know, where does K go from being approximately 1 to large? Well, it's a continuum, right? But the larger K is, the more the forward reaction is favored. When you get K approximately 1, then you have a more balanced equilibrium, where the forward reaction proceeds roughly halfway. If K equals 1, you're going to have equal amounts, right? So the closer to 1, the more equal the equilibrium becomes. Now we're going to look at the relationship between the rate constant and the rate constant expression and the actual chemical equation. So if we change the chemical equation, then we have to change the rate constant. And so there's 3 common situations that we'll see, and we're going to go over those. So if you reverse the equation, what you do is you invert the equilibrium constant. You don't just slap a negative sign on it. You have to upside down it. It's 1 over. So let's look at how/why that is. So here we have the forward reaction. A plus 2B is in equilibrium with 3C. And this is what would happen if we reverse the reaction. We're just writing it backwards. We're flipping reactants and products. So K forward is going to equal what? What goes on top? C cubed, products over reactants, right? A times B squared. And K reverse for this guy, now we're going to have these being the products, so we're going to have A and B squared divided by C cubed. So K reverse equals 1 over K forward. You see that? We take this and we turn it upside down, and we put the denominator on the top and the numerator on the bottom, and that's the equilibrium expression for the reverse reaction. The equation written backwards, okay? If you multiply the coefficients in the chemical equation by a factor, then you have to raise the equilibrium constant to the same factor. So here we have that same reaction. So we said that the equilibrium constant was C cubed over A times B squared. And here we're multiplying all the coefficients by some number n. Still a balanced chemical equation, right? Because we did the same thing to everything. We're multiplying by some number n. So what's the equilibrium constant expression here? You take the concentration and you raise it to a power equal to the coefficient. So that's going to be C to the 3n power. We don't know what n is. Could be 1, could be 5, could be 17.4637. Probably not. Why would you do that? And then this would be A to the n and B to the 2n. Everybody okay with that?
Yeah.
I'm writing too big. Well, that is equal to C cubed over A B squared, the whole thing raised to the n power. Everybody okay with that?
Yeah.
Let's call this K prime, and we'll call this one just K. So this equals K to the n power, doesn't it? This part in here was our original equilibrium expression. So this is K prime is equal to this. So if you have a chemical equation and you know what the equilibrium constant is, but say you've got the whole thing doubled, then you square the equilibrium constant. You don't have to go through all of this and calculate everything again. You can just look at, oh, I doubled all of the coefficients, I'm going to square the equilibrium constant. Because a lot of chemical reactions, you can go to a book or the internet and you can look up what the equilibrium constant is. You don't actually have to do an experiment and measure all kinds of junk, because other people did that for you. Nice? Another thing that might happen, if you add two or more chemical equations, typo, needs to be an S in there, to obtain an overall equation, you multiply the corresponding equilibrium constants to obtain the overall equilibrium constant. So let's see how that would happen. Let's say that we're adding these two reactions together. Here we have the equilibrium constant for this first reaction, the equilibrium constant for the second reaction. When we add these, those guys, the two B's were formed and then they got used up. And so we end up with A being in equilibrium with 3C. Everybody okay with that? And looking at this, what would the equilibrium constant be? Let's call that K3. C cubed over A. So what this is telling us up here is to get the equilibrium constant for this one that we got by adding these, we should take these two things and multiply them. So that's telling us that K3 will be equal to K1 times K2. So K1 is B squared over A, and K2 is C cubed over B squared. And what happens to the b squared? They cancel out. B squared over b squared is 1. And we're left with c cubed over a. This sort of thing can be really useful if you're looking at, say, a reaction mechanism or a sequence of reactions where you have the measured equilibrium constants for each of the steps, but you don't have it for the final result. Do you remember Hess's law from 1A? You can find the energy of a reaction by adding reactions that you know to get the final reaction you're looking at, because the final energy and the initial energy are independent of the pathway. And so if you were to do something like that and you were dealing with equilibrium constants, you just multiply them when you add the equations.